I can see in your eyes there's some questions here. Now we're going to get into the ductwork itself. There's a whole bunch of other components that are going to be connected to this, that each one of them are going to contribute some energy loss that we have to make up in one way or another, usually by designing them out or by sizing the fan to move the amount of air that we have to move. Okay, what do you say we take about a 5-minute break? Because I can see that you might have a couple of questions, and you seem to be ready for one, right? Okay, let's take a 5-minute break, and I'll answer some questions if you have them. Okay, Brittany, how are you doing? Do you need? Oh, good work, Brittany. You're keeping up. Do you have any questions? Okay, good. I'm going to pause this. I'm going to pause this for a couple of minutes, Brittany. Yeah. Okay, guys. No, we were having a little bit of a discussion, side discussion here. So it wasn't that the audio wasn't working. Okay, guys, now you should be able to hear me now. Okay, good. Grace, can you hear me now? We were having a debate over which of these formulas to use for Q. Okay, one of them is based on the idea of a hemisphere around the opening of the hood or the duct and how much air is being pulled in. And this one that's unflanged has this larger hemisphere of air being pulled in. And the formula for this one is similar, but it's 3 pi instead of 4 pi because it's only considering a true half sphere or hemisphere of air being pulled in. So the second formula actually does incorporate the area of the opening in the ductwork. So I prefer using that. It's less conservative. It gives you a lower number as we calculated than the former. But we'll take a closer look at that as we go forward to decide which one we think might be the best one to use. Okay. So at any rate, let me go back to what we were doing. Okay. Sorry to exclude you there for a little while. We forgot about you. Not really. We just got off on a tangent. Oh, no. Okay. So you gave me the hook. That's the first time you gave me the opportunity to start from scratch. Okay, so we have many other components that we're going to be dealing with. Okay, let's talk about ductwork. We need some way to move this air. We're pulling air into the hood. We have to move it outside of the building into other areas and so on and so forth. We need a conveyance structure for this, and that, of course, usually is ductwork. Typically, it's round ductwork because when the systems that we're working on, the important parts of them are under a negative pressure. A lot of times they're under a large negative pressure if we have to pull a lot of air. So circular ductwork is structurally more sound. It's less likely to get collapsed than rectangular ductwork is. There are going to be branches in it. There's going to be components that we're going to have to deal with. There's going to be transitions, contractions, expansions that are going to be necessary as we run the system. And there's also going to be places where we're going to maybe connect to other parts of the system. Maybe we'll have more than one duct, one hood on an exhaust system. Maybe we have many hoods on an exhaust system. So we're going to have branches and intersections as well. Well, we want this stuff to last because although there may be components of the fan that may be replaced or maybe even the whole fan itself, the ductwork pretty much is expected to last the life of the system. We want it to be structurally sound. We don't want it falling apart. We don't want it leaking. On the suction side of it, leaking is less of an issue. That's an energy loss if you have it, but since it's under a negative pressure, it is unlikely to allow contaminants out. On the discharge side, though, leaks can be a real problem if they are discharging material from them. We want to avoid the deposition of the contaminant that we're capturing. Of course, if it's a gas or fume or something like that, it's less likely to be a deposition issue than, say, coarse particles. Coarse or larger, heavy particles are. So in our charts and tables, our references, we're going to find reference to velocities that we should maintain in order to keep the contaminant, the heavier contaminants entrained in the air flow so that they don't wind up settling out in portions of the system and winding up being damaging the system, interfering with it, the operation of it, or necessitating a dangerous or costly clean out of the system. Okay, so that's transport velocity. Okay, for dusts, particulate material, generally you'll see them in the 4,000, 5,000, 6,000 feet per minute range. Too high a velocity may increase in a lot of turbulence, and we know the velocity is related to the friction, right? So the higher the velocity is, the more your friction losses are in any of these in any of these structures, whether it's the ductwork itself or the hood. We saw that hood entry loss is related to the velocity pressure, the speed that the air is moving through. What else happens if you get too much, if the air is moving through too fast? Pretty noisy, right? You can get vibration, noise, all sorts of nasty stuff. Too low a velocity will result in deposition of the dust from the duct, especially in areas where there may be turbulence, like at transitions and so on and so forth, or where the velocity may change from a fast, where it's expansion, where the duct is expanding, and the air flow may actually slow down a little bit. Duct material should be abrasion resistant and smooth. Usually, unless it's a corrosive material, for the most part, you'll see people using galvanized iron because typically it's the cheapest and easiest to work with. Vapors or gases recommended 1,800 to 2,000 feet per minute. Flammability should be considered if it's a gas. In fact, I mean, dust can also be flammable and explosive, right? So I think you really have to consider that with any of these things. Okay, so let's see, scrubbing velocities for dry particles. Okay, so these are the as we get into larger and heavier particles, right? This is an example of some of the velocities that you might want to maintain. Obviously, fine or light dust, you need a lower velocity to keep them entrained. Heavy dust, you need a higher velocity. Oops. Okay. Okay. So let's talk about duct losses, duct friction losses. We're losing energy. Remember, our static pressure is our potential energy. It's what causes the air to move through the ductwork, get pulled through the ductwork, and generates that velocity and that velocity pressure. Okay. So now, if we have, you can imagine, if we have a long run of ductwork, we're going to have a greater loss to friction. The roughness of the duct, the material of the duct, the roughness of the duct is also going to impact on how much frictional loss we have through the duct. So we have a simple formula. The friction loss due to the duct is equal to a factor K, this is not a hood factor, this is a different factor, times the velocity pressure, times the length of the duct, right? Times a R is a correction factor. We're going to take a look at that in a second. And D is a density correction factor. Again, density correction factor for our purposes right here, I'm going to ignore. It's equal to 1 because we're at sea level and we're dealing with room temperature. But if we're dealing with a duct system in Denver, Mile High City again, then we may have to include that. In fact, I have a brief problem here where I ask you about that, and we see what kind of impact that can actually have. So let me see if I can't pull up chart number 4. Well, actually, I'm going to go ahead and work through a problem so we actually employ this formula. But look at this. It's a factor times the velocity times, except this time the only thing that we've added, the K and R are related to the material of the ductwork, right? They're factors that are supplied to us based on what we're using, right? The velocity, again, I lost my mouse again. The velocity and the velocity has a function here, as does the length of the ductwork. So we have some sort of combination of constants. We have the velocity and we have the length of the ductwork. That tells us how much friction that we're going to have, how much loss we're going to have. Okay, so let's go ahead and actually do a calculation there. There's a couple of types of ductwork that we might be dealing with. Okay, so there's various correction factors for some of these materials. For instance, corrugated flex duct, there's a lot of friction associated with it. You've ever seen it, it's got these ribs in it, and it's got a very uneven interior surface. If it's not well supported, it bends and kinks and so on and so forth. So there are correction factors for some of these materials other than galvanized iron. The assumption is that you're going to use the most common material, galvanized iron, so the correction factor is 1 for galvanized iron. Okay, K is the loss factor for ductwork. R is the correction factor for the material that you're using. It's usually associated with the roughness of the interior of the ductwork. Okay, so let's take a look at this. Standard airflow in a galvanized iron duct at the, let me move this over. Galvanized iron duct at the velocity moves at the velocity shown below. What is the correction factor? The friction loss factor, K. The actual loss in the length of duct. Okay, all right, so let's take a look at this. We know we're going to use charts 5 and 10. I mentioned that here. Okay, and we're going to do it now for galvanized iron, and then we're going to repeat it for ABS plastic. ABS, you know ABS plastic, right? That's the stuff they make Legos out of. It's not PVC. It's another material, right? But it's not unusual to use it in lab systems. Okay, so the friction loss is equal to K. Well, let's get up table 5 and 10 first. Let me move this out of the way so we can look at those tables. Here's table 5. Okay, so now table 5. Why am I looking at table 5? Well, let's take a look at this. First of all, table 5. Remember we did all those calculations with that involved converting velocity and velocity pressure? What we could have done is just go over to this table. So for instance, 2,000 feet per minute is the same thing as about 0.26 inches of water, right? That chart does the same conversion as that formula does. So you could have just gone to this. Well, now you know how to do it. So you know when you go to, see, if you just went to this chart, you would say, oh, the only way I can do this is by looking at this chart. But this is really based on that formula. This is called a nomograph, right? And since it's a simple equation, it's a simple nomograph. So all you have to do here is that, for instance, if you have 5,000 feet per minute, is a velocity pressure of, looks like 1. Hardest thing is reading the, well, it looks like about 1.65, 1.6 or something like that. It's accurate enough for the kind of work that we're doing here. Okay, so now I'm interested in, let's see, chart 5. What else is in here that can help me out? Duct friction losses. Now, the friction losses are related to the area of the ductwork, the size of the ductwork, and the amount of air that you're moving, right? Here's the amount of air that you're moving. The amount of air moving and the area, cross-sectional area of the ductwork, that tells you what the velocity is, right? This scale and this scale work together to tell you the velocity. And this scale tells you the duct friction losses, right? That's your K per foot, right? So let's take a look at what we know here. We know, what have they told us here? The velocity is equal to 2,000 feet per minute. The duct diameter is 18 inches. Okay, let me see what we have here. Okay, so the volume flow rate, let's see. I got the velocity over here. So I can go over here. I can go to Tools, Annotate. I need to get a line. You could do this with a ruler, right? And I'm going to draw a line between, what was it again, 2,000 feet per minute? Did I get that right? 2,000, was it 2,000 feet per minute? And what was the 18 inches? Okay, I'm going to draw a line between the two of these. Okay, and where it crosses this duct friction loss line, first of all, number one, the volume flow rate is going to be, looks like roughly, let's see, 3,500 cubic feet per minute. And the friction loss is going to be about, now the scale goes up as you go down. So 0.0, let's see, 0.01, 0.015, 0.01, let's see, this is 0.010, and this is 0.105. So this looks about 0.011 to me, right? So the duct friction loss is 0.011. So K is equal to 0.011. The velocity pressure is equal to 0.25. The length is, what's the length? 50 feet. R, we're using galvanized iron, so what's R? 1. Sea level, so what's D? 1. So what does that friction loss come out to? I was talking, so I wasn't doing it. So unfortunately, you ain't going to get any help from me. What was that? 0.14 was it? Oh, guess I'm going to have to get involved. K was 0.011 times 0.25 for the velocity pressure times 50. Do you have an opinion on that now? How much? 0.14. 0.1. The loss of static pressure. The loss of static pressure in this ductwork, 50 feet of this ductwork, is 0.14 inches of water. So if we know what the static pressure at the back of the hood is, right, whatever it happens to be, now in order to keep the air moving, we have to have that much more static pressure 50 feet further up, because you would have lost 50 feet of static pressure from that point down. Does that make sense to you? Let me sketch that. Where'd my notebook go?
What's the units for this?
I'm sorry.
The units?
Inches of water. Okay, so what have we done here? Okay, let's say that we had a hood here. Okay, here's our hood. Okay, and here's our ductwork. Now our hood static pressure, right? Our hood static pressure. Let's say that in order to get the capture velocity that we wanted, we calculated that that has to be 1 inch, negative 1 inch, right? Well, now if I add 50 feet of ductwork to this thing, right? I'm going to lose 0.14 inches of static pressure across that ductwork. So the static pressure at this point has to be this plus the 0.14, positive value of that plus the 0.14. So let's say, so it would have to be 1.14, because I know I'm going to lose that much between here, suction pressure between here and here. So what are we looking at here? The hood entry losses. We're losing static pressure there. 50 feet of ductwork, we're losing static pressure there. As we move up this chain to the fan, we have to keep calculating how much each component would lose us in terms of energy, particularly in terms of static pressure, right? And now we know how to do it for the hood, and now we know how to do it for the ductwork. So if you have a length of ductwork here, and then a turn, and then a 100-foot length of ductwork, we know how to calculate at least what the ductwork is going to cost us in energy. Okay, makes sense? Okay, not that hard, right? Right? Especially since you have all these tables to do a lot of these calculations. That's why I didn't want to introduce it to you right too quickly, that table, because I know it would it's like a little bit too tempting to use that. Okay, let me see. Let me hit play. Okay, so yep, I'll look at that calculator. You guys were right. Okay, so now I'm going to ask you guys to do the same thing again. Okay, except this time you're going to do it for ABS plastic. Okay, and in this case, standard airflow, whoops, that should be changed. Ignore galvanized iron. You're doing it for ABS plastic, duct. At the velocity shown below, what is the correction factor? What's the friction loss? What's the actual loss in the length of duct? Again, use the same charts. And the velocity is the same, diameter is the same, the length's the same. The only thing that's changed is the material. So you're going to be changing your R. Okay, guys. Okay, so what's K? K is the same thing we calculated before by using that chart, by drawing a line between the velocity. Why does it keep jumping like that? Oops. Oh, it took a big jump that time. There we go. Okay, before K was, how do we find K again? We found K by drawing a line between the cross-sectional area of the ductwork, 18-inch diameters, 18-inch diameter ductwork, and the velocity or velocity pressure that's running through the ductwork. And that line intersected the volume flow rate, tells us Q if we wanted it. In this case, we don't need Q. Tells us also the duct friction loss coefficient, that K. Now, the faster it's moving, notice that if the velocity is higher, if the velocity is higher, let me move that back down there. If the velocity won't let me move, I think I didn't get it that time either. I can't get it to stick. I'll tell you what, let me draw a new line. Here's 18 inches. Our velocity was 2,000. Okay, now watch this. If the velocity is higher, what's happening to K? K's going up, right? Right? If the velocity is 1,000 feet per minute, it's going down. But as the velocity goes up, K goes up, right? Oh, you're right, it's going down. Does that make sense? Let me think about this. Velocity, K. That's odd. I would have thought it was the other way around.
It's less friction. It's more friction.
Well, no, maybe as it's moving through, the duct side effect has more of an effect on it. That could be. Yeah, it's not necessarily more friction. Well, not only that, but you also have to consider the fact that the formula also includes the velocity. So K may be going down, but the velocity is going up faster. So overall, there's more friction. Right. Well, remember the velocity is going up. See, this may be going down a little bit, but that's the velocity pressure is going up faster. Right? Okay, so what'd you get? What's the only difference? The only difference is you're multiplying by R. What is R? 0.9, so it's whatever, it was equal to 0.014 times 0.9 then in that case, right? Or about, you lost a little less pressure. You lost a little less static pressure. Why would you lose less static pressure in the ABS duct? Because it's smoother, right? Plastic duct is going to be smoother than that metal ductwork is. Okay, so let's move on. How are we doing on time? Why is that doing that? Oh, that's you. Okay, I thought it was me. All right. Good. Brittany, you still there? I like testing Brittany, make sure she's still awake. Okay, good. Okay. All right, yeah, in fact, that kind of makes sense now. I'm kind of surprised that K value goes down a little bit. Remember, it's all the way over to the left, so the angle that it's moving, it's not changing as much as the velocity is changing, right? But the velocity is going up quicker than that K is going down. Okay, so that may make sense. Okay, still, as the velocity goes up, you have a greater loss. In any case, expansions. The next kind of transition that we have to worry about. Now we got a hood, we got the ductwork. Now the ductwork may not always be the same size all the way through, so you have transitions that you have to deal with. Ys, Ts, Ls, so on and so forth. Most common one, especially in ductwork where you only have a single hood, it's going to be elbows. Every once in a while, if you go across, you go up, you're going to have to go across and then up and around and out the ceiling, make a turn into a fan or something like that. So elbows are very common. The considerations that we have with elbows is mostly got to do with how fast it turns the air. What the ratio is between the diameter of the ductwork, size of the ductwork, and the radius of the turn, right? So the bigger the radius of the turn is, the less loss that we have. If you can imagine, if we're just like a quick 90-degree turn, it'd be an enormous amount of the air would just go slamming into the other duct and into the turn, and there'd be an enormous amount of turbulence and energy lost. But the more gradual the turn is, the less that we have in terms of energy loss. Now, most metal ductwork is assembled out of sections. Most of it is not a regular smooth transition like you might get with PVC or ABS plastic or something like that. Most metal ductwork, they have transitions. You'll see a picture in a second. It'll look quite familiar to you. Okay, so for instance, the first example of elbow on the left is smooth. That might be what you might get, if you had PVC or polyethylene or ABS or some other kind of plastic ductwork. More likely, you're going to see either a 3, 4, or 5-piece turn. You go to Home Depot right now and you look for something to exhaust your dryer or your boiler vent or something like that. You're going to find this kind of ductwork there. The plain right angle, what they call mitered there, okay, that loses the most amount of energy. The smooth elbow transition loses the least amount of energy, and the others in between, the ones that are closer, as you have more and more pieces, it's closer and closer to that smooth transition. The other factor you're interested in is the ratio of the diameter of the pipe, diameter of the duct to the radius of the turn. So, and you can imagine, the bigger that ratio is, right? Like in other words, let's see what we got. We can have a ratio. Let's see, a 3-piece duct. You have a ratio of say 0.5, where the radius, the diameter of the duct, 3 pieces 0.9 or pretty close to 1. The radius of the duct might be, let's see, the diameter of the duct might be 1 foot, and the radius of the turn might be 1 foot, and that would be a ratio of 1 to 1 or just 1. So that would be something like this at this end here. Okay, so now let me see if we can't apply this and make some sense out of it. Okay, we're going to take one of these elbows that's shown in this strange configuration of 2 hoods that are joining up into a single hood. We're just going to look at the elbows. We're going to look at elbow C and elbow E. One's at the top, one's at the bottom. Okay, calculate the loss from elbow C, a 3-piece. R over D equals 1.0. In other words, the radius of the turn is the same as the diameter of the ductwork. It's 1 foot radius turn, and it's a 1 foot diameter ductwork, for instance. And it's a 90-degree turn. There's a trick about this. All of these charts assume a 90-degree turn, but there's a way for us to adjust for that if it's not a 90-degree turn. Okay, so the velocity that's going through this ductwork is 4,000 feet per minute, and the duct diameter is 8 inches, and we want to calculate what the loss is going to be. Okay, so the static pressure loss is going to be equal to some factor for that particular elbow times the velocity pressure, times, again, density correction factor. Very similar to all the other, the hood static loss pressure, the duct static loss pressure, so on and so forth. The only difference here is we've got a new constant, a new factor that's going to relate the velocity pressure to the static pressure. Okay, so static pressure is going to be equal to, the K factor is 0.42. Let me see if I can't pull up chart 5 again. Let me see. I think that is on, see if I can find that one. Elbow loss factors, chart 13. Okay, so what did I say the ratio was? Was 1? Was 1. And how many 3-piece? Here's, whoops. Okay, so R to D is a ratio of 1. And we have a 3-piece elbow. It's 0.42, 3-piece elbow. So the factor, the friction factor is 0.42. Had that been a 5-piece, same ratio of radius to diameter, it would be a lower friction factor. We'd have less friction through there for a given velocity. Had it been a smooth transition, it would have been the least, right? So, and had it been a slower turn, here it is, had it been a three-piece but a slower turn, ratio of the radius to the diameter is what it was higher, say 2, it would only be 0.33, that K factor, that loss factor. Okay, so in our case, it happens to be 0.42. Okay, so I'm going to go back here. So K for the elbow is equal to, loss factor for the elbow is equal to 0.42 times the velocity pressure. Okay, now the velocity pressure, I can go 4,000 feet per minute. I'm going to go back to table 5. Okay, 4,000 feet per minute. Okay, that's roughly a velocity pressure of 1.01 inches, 1 inch of water. A lot of windows open here. I need a bigger screen. Okay, it's equal to times 1. So the static pressure loss at that velocity going through that turn is 0.42 inches of water. Right? Not hard to calculate it. Right? So what's the next step? You're going to do one, right? Next step is you get to do one. Yours is going to be 4,000 feet per minute, except your duct ratio is going to be 2.0, and it's going to be a 45-degree turn, not a 90-degree elbow. So what do you think you might do there with your factor? Okay, let's look up what that factor is first. We're looking at R over D equals 2, right? And 4 pieces. So what is K? R over D is 2, and it's 4 pieces. What's K? 0.24. What do you think we might want to do for a 45-degree turn versus a 90-degree turn with that K factor? Take a wild guess. Bingo. There you go. Divide it by 2. It's half of a 90-degree turn, so you just divide it by 2. If it were a 30-degree turn, right, that would be only a third of the turn, so you divide it by 3. Okay. If we're a 60-degree turn, you would multiply by 2/3, right? If we're a 60-degree turn, because you're making most of a turn, right? So you would adjust that K factor for this. Now, are all these calculations, these K factors, these calculations for static pressure loss, are these all look like precise, exact calculations to you? Probably not, right? They make a lot of assumptions. A lot of them are worked from tables, that general tables. So that's really what they are, is estimations, right? So, but they help us. They're tools that will help us figure out what's the most likely sizing that we need to have on the ductwork, on the fan, on the components, and so on and so forth to achieve what we want, which is ultimately to get that capture velocity that we need at the end and keep the air moving so we can get it out of the building, right? So what's going to happen for you guys now? Okay, so your static pressure loss is going to be 0.1 instead of 0.24, 0.12 times the velocity pressure, which was 1, and the density factor, which was 1. So it's going to be 0.12 inches, right? Everybody agree with me on that? Okay, good. You guys look tired. Okay. Okay, a little bit. That's a little bit description of what we're talking about the radius and the diameter. Okay, transitions. We're not going to go through transitions right now. We're probably almost out of time anyway, right? We're pretty close. We're not going to go transitions right now, but if you can imagine, there's a few issues with transitions. If we're adding in something that tees into this ductwork, it's going to bring more air in that we have to pull. So the size of the ductwork to maintain the same velocity is going to have to increase. So generally, they actually join in a transition where you have a smooth transition from one duct to another that gradually increases in size. You want to avoid like these butted ducts and stuff like that, because if you can imagine, anything that you can imagine that's going to cause turbulence is going to be an issue and increased friction. Okay, now here's just a reminder that in ductwork, you're not going to see this too often in practice, but in ductwork, you may have changes in the size of the ductwork, and when they get a change in the size, keep in mind the quantity of air is always the same. If you got 4,000 cubic feet per minute coming into the hood, you got 4,000 cubic feet per minute moving through every part of that ductwork, right? Because otherwise you're going to have a vacuum or you're going to have a lot of air piling up somewhere. So as the ductwork gets narrower, it's got to move faster. Ductwork get wider, it's got to move slower. So Q equals V times A is always going to be a way for you to figure out what the velocity is, because the quantity of air has always got to be constant through the whole system. Okay, here's an example of this is on the on Blackboard, and you have this, a copy of the PowerPoint as a PDF. But with transitions, let's see. On this one, Q is equal to the quantity of air is moving through this 4,500 cubic feet per minute. It's going through a contraction. Now the velocity is going to change. Went from 2,500 to 4,200 feet per minute. The inlet static pressure was 2 inches. What's the static pressure loss? There is a formula for figuring this out. There's a K value for this kind of transition on chart 17. Okay, I'm not going to go through this particular one right now, but there is K value. You go to chart 17, you get that K value, and it's based on the change in velocity pressure, because you have one velocity, you have another velocity. And how dramatic that change is really what affects how much energy that you lose there. Here's part of that chart. Okay, so for this, and it's got to do with the angle of that transition. Bigger that angle is, the bigger the loss is, the bigger that K is. Okay, and you have other transitions. Flex duct, we already talked about, was miserable for anything. It kinks and bends. Usually it's 10 times the length that they actually need because they never cut the stuff. This is a blower for supplying, I guess, outside air for a confined space or something like that. Okay, and next time you go into a building where the ductwork is exposed, right? Most exposed ductwork is going to be galvanized iron. Look up and take a look at some of the transitions that you see there. Okay, so you have transitions. Rectangular duct, very frequently you're going to have to transition from a rectangular duct to a circular duct to run ductwork to other locations, or to combine it with other duct and so on and so forth. So you'll see a lot of these transitions. Okay, and they'll have their own sets of losses. Most local exhaust systems are designed to are automatically balanced by design. In other words, you turn the fan on and the ductwork, the transitions, all of the connections are all sized so this hood gets the right amount of air and all the velocities are right throughout. Many other systems, occasionally some duct systems, some local exhaust systems, use dampers. This is called a blast gate. All it is like a piece of metal that drops down into the duct, and you can use it to adjust the airflow through the duct, right? Now, that introduces enormous inefficiencies, so you don't see them that much in the kinds of exhaust systems that we're trying to design. However, you do see them in these systems, right? Because they have to design them for the future. They have to anticipate changes in the usage in these buildings. So these diffusers that are over our heads, many of them have dampers, not like this, but they're more like a kind of a butterfly kind of damper. Many of them have dampers. Some of them have motorized dampers on them that can regulate and change the flow of air coming out of each one of these diffusers. This system is designed to use them to control the temperature in the room. They regulate how much air comes in here. But some of them actually have to be, some systems that are constant volume systems, they're only set once and left, and they're designed, those dampers are designed to make sure the right amount of, an even amount of air is going into each room. And you can imagine that, gee, why don't they just simply design the ductwork so that happens automatically? It's conceivable they could do that. But they have to anticipate changes in like how much space is occupied and so on and so forth. So frequently they'll design them with these adjustments. Blast gates and these kind of dampers and stuff like that, we usually want to avoid them in a duct system. Now, one of the things we're going to be doing in the future is that we're going to actually, as we start to assemble these things, we're going to analyze what goes on with the static pressure. Now, remember we said static pressure was got to be a certain amount at this point just behind the hood. And then it had to be a little bit higher, that negative static pressure, because we had to make up for 50 feet of ductwork. Then it had to be a little bit higher because we had to make up for an elbow. then it'd be a little bit higher, and so on and so forth. You got to make up for something else. This is a charting of what the static and total pressure is throughout a duct, throughout a system, and you can use this as a tool to design the system, look for places where there are larger losses or smaller losses, and so on. Okay, I think that's it for tonight. I'm starting to put together an